Good morning, everybody. If we can go with some green check marks, please, we'll get started. I would like to go over anything you guys had in terms of questions from the radioactivity section, 7.1. So we had a bit of an introduction to radiation. We looked at alpha, beta, gamma. Those are kind of the big thing, was the three types of radioactive decay for those really unstable nuclei. Today I hope to get into half-life. We'll probably only be around for about an hour today. And then I think there's one more section for this unit, which we'll cover next Tuesday. That's number 6 out of 7.1, Eric, I'm assuming. Okay, let's have a look. My pen wasn't working this morning, so I might not be able to help you as much as I'd like. If you have the same two isotopes, two isotopes of the same element, what subatomic particle will they both have the same number of? So number 6 kind of asking in terms of subatomic particles. So what are the subatomic particles? We have protons, neutrons, and electrons. Now this question is asking if we have two elements with they're the same element. Two isotopes of the same element, what particle will they both have the same number of? So if we're the same element, we're always going to have the same number of protons. That's what defines an element. 1 is hydrogen, 2 is helium, 3 is lithium, 4 is beryllium, 5, 6, 7. As soon as you change the number of protons, you become a new element. So isotopes all have the same name. We can talk about carbon-14, we can talk about carbon-12, we can talk about carbon-13, but they're all carbon. And what makes carbon carbon is the number of protons it has. So my pen's not working, but protons are always the same. And Carla wants number 13. Can do that. Maybe I still have it done from last year. This table here, Kyla. So this is just kind of a summary describing the three radioactive decay particle things that we talked about last day. So alpha, beta, gamma, particles or rays, description, and what can block them. I have a feeling there's a table. Oh, it's not in the learning guide. I tell you what, I'll just jump back to the table I have from the notes from last day. I believe there's a little summary here. Isotopes. There we go. So the chart behind me here has the summary. Yeah, I think everything's there. So these are the 3 different types. Remember, alpha is just a helium nucleus, 2 protons, so it has a charge +2. Beta is a high energy electron, has a charge of -1 because electrons have a charge of -1. And then gamma is just rays of energy, electromagnetic radiation. Doesn't have any mass at all. Charges are there, 2, -1, 0, blocked by paper, blocked by metal foil or concrete, and then something like gamma, you need some lead or some thick concrete to stop those guys. High energy. Is that what you're looking for there, Kyla? Perfect. So we got 6, we got 13, and we want to look at number 8 as well. So, jump over to number 8. All right, so number 8 was talking about the 3 different isotopes of carbon. We actually did this one last day, I believe. So when we talk about isotopes, we're talking about the same element, so in this case carbon, but the carbon has different mass, and the different mass means that you're changing the number of neutrons. We can't change the number of protons, because if we change protons, it becomes a new element. But if we change the number of neutrons, it's what we like to refer to as an isotope. So carbon 12, carbon 13, carbon 14. You'll see this kind of shorthand for isotopes. And this is the element, which is carbon, followed by the atomic mass. Now, we know carbon always has 6 protons. That's carbon, that's number 6 on the periodic table. But the 12, the 13, and the 14's indicating the mass of it. So carbon 12 is going to have a mass of 12. 6 of those are protons, 6 have to be neutrons. Carbon 13 has a mass of 13. 6 are still protons. Now we have 7 neutrons. And then carbon 14, we're actually going to spend some time looking at carbon 14 today. Carbon 14 has a mass of 14. 6 are protons. Leaves 8 left for neutrons. So there you go. Beautiful. And that's essentially what isotopes are. With the symbols, we need to write the atomic, if I can write it, if I click, let's see, maybe. At the top of this, we write the mass. So we'd put get a text box in the right spot. It's not going to work very well. We'd put a 12 at the top, because that's 12 for this guy down here. We would put a 13 at the top, and for this guy down here, it's not going to ever be in the right spot, close enough. We'd put a 14 at the top. Kind of like you see down below on question number 9, with the mass at the top and the atomic number at the bottom. No worries, Costin. If you have more questions, I'd be happy to go through them. If you have 2 isotopes of the same element, what atomic, subatomic particle they always have different numbers of? So for number 6, we said the element would have the same number of protons. For number 7, what's going to be different? What are we thinking? What's different in the chart down below? So number 8, we looked at carbon specifically. The number of protons is the same for all 3 rows in the chart. Which one's different? Yeah, Costin, neutrons. So your neutrons is what makes an isotope. So if you have, carbon, it always has 6 protons. You can't get around that. If you go to 7, you're nitrogen. You're not carbon anymore. So you always have to have the same number of protons, but the neutrons can go up and down. And that's what defines an isotope. Is there anything else that we would like to look at prior to going into 7.2 on half-life? Alrighty. So, my background's all shifted here. Looks a little bit better. So half-life is a concept that has to do with radioactive decay, and it kind of takes a little bit of the ideas of the decay we talked about last day and kind of puts a time limit on things. And we can do a lot of really amazing things by knowing the half-life of elements. Does anyone have any preconceived ideas of half-life? Normally when we think of radiation, we think, oh, radiation's bad and it hurts us and it's just terrible. Half-life, generally students have one, preconceived notion of half-life, because their only interaction with it has to do with, anyone ever heard the term before? Anything to do with half-life? Usually students think of like a video game. There's a video game called Half-Life. And I've never played it. I think it has to do with some like post-apocalyptic world where everything's kind of radioactive. Um, but yeah, I have no idea. Never played the game before. Jesse, that's good. What I will maybe change with your definition, because a lot of people kind of, I don't want to say struggle with the concept of half-life, but in your definition you said how long it takes for an element to, I assume you were putting in like lose or 50% of its energy mass. So the idea behind half-life is kind of misunderstood. It's atoms are actually changing from one thing to the next. You're not losing anything necessarily, it's just changing. So the amount of time it takes to change, half, 50%. That's what we're going to talk about today. So you're right there, Jesse, you got it. Why do we care? Well, when we look at something like this pen, and I want to figure out how old it is, I don't know. I have no idea how old this is. And a lot of things we can figure out the age based on, well, this pen came out of, this computer, and this computer model is, what is this? This is a Yoga 460. And Yoga 460s didn't, get produced until 2017. So the pen's probably made in, 2016 or 17. We can do stuff like that. But when we start talking about really old things, it's difficult to put dates on things. If I just had a rock here, I said, how old is this rock? Well, how are you going to figure out how old a rock is? So what we can do is use the ideas of half-life to look at how much stuff we expect to be there and see how much stuff is actually there, and then we can compare the amounts and determine how old something is. So this works with for really large time scales. And probably the most common one you'll hear of is carbon dating. Now, every living thing on Earth contains carbon. That's just all life on Earth is carbon-based. So anything that is living or was once living has carbon in it, generally speaking. And we can look at the amount of carbon that's in something and figure out a pretty good estimate of how old it is. Costin, I don't come up with the learning guides on my own. They just come with a course. So I do understand that they are a little bit different in this particular one. It happens in all of the courses for whatever reason. So I did my best to kind of match the slides up with the questions that are here. So it says half-life, there are two isotopes that we can compare. So all of these questions will end up popping up at some point in the notes until we get down to some of the other stuff at the bottom. So just do your best to kind of read the question and then see if you can write down the answer. And if you do have a question, like if you think I've skipped something, you can just say, hey, Mr. Borden, I didn't get number 2. And it's likely it'll either appear or we can go find it. So carbon in your body right now, you have carbon in your body. You're made of carbon, water, some other stuff. You have carbon in your body. Most of the carbon in your body is carbon-12. 99% of the carbon, or sorry, 98.9% of the carbon in your body is carbon-12. There's a little bit of carbon-14 in your body, a little bit. And this carbon-14 is radioactive. It's unstable, which is the same thing as radioactive. It wants to become stable. It wants to decay. Decay is the word we use when something goes from something that's unstable to stable. So it wants to decay into something that's stable. Now, every 1 trillion, like 1 in a trillion atoms in your body are this carbon-14. So when we think about how many cells you have in your body, you have millions and millions and millions of cells in your body. And each one of those cells is made up of, smaller parts. And each one of those smaller parts is made up of things like DNA, and DNA is made up of atoms. And these atoms are made up of carbon. And so you do have a little bit of carbon-14 in you, not a lot, but enough that we can actually find it. So if you kind of think back to the carbon cycle we studied when we were looking at the biology unit, when something is alive, like I'm alive right now, at lunch I'm going to go eat an orange, and that orange is, you know, carbon, it's a living thing. When I eat it, the food goes into my body, my stomach digests it, my intestine absorbs the food, the carbohydrates, which are just long carbon-hydrogen chains, that sugar in there. It takes it to my cells burn it as energy. Some of the carbon gets exhaled, some of it gets used in my cells. So when I'm alive, I'm constantly eating and I'm replenishing the carbon in my body. I forget how long it takes to replace basically all the cells in your body. So over your lifetime, your cells are going to die and be replaced with something new. Your cells are constantly replenishing themselves. So as long as I'm alive, I'm eating, I'm replenishing the carbon in my body. The amount of carbon is completely being replenished all the time. But when I stop eating, when I die, the second I die, I'm no longer taking in carbon. So the amount of carbon that's in my body is now fixed. I'm not taking in anything new. I'm not putting out anything. There's no more carbon cycle going on in my body, essentially. So what we can do using something called radiocarbon dating is once something's old and dead, or something that was formerly living, we can look at how much carbon-14 is there. And carbon-14 breaks down into nitrogen-14. So we can compare the amounts of carbon-14 and nitrogen-14, and we can get a good indication of exactly how old something is. We know very accurately that carbon-14 has a half-life of 5,730 years. That means if I had a cup full of carbon-14, full, all the way to the top, after 5,730 years, half of it would have decayed into nitrogen-14. So I'd have a cup that had some nitrogen, I'd have a cup that had some carbon. It's really, really important to think about this in terms of something changing. When I have this full cup of carbon-14, and after 5,730 years, half of it is, sometimes we say it's just gone. It's not gone, it doesn't just disappear. It's changed from carbon-14 into nitrogen-14. So now my cup has some carbon in it, it has some nitrogen in it. If I wait another 5,730 years, that half of the cup that carbon-14 is now changed into nitrogen-14. So now I only have a quarter of my cup. And I can keep taking half-lives, 50%, 50%, every 5,730 years. So what we did with this cave painting here, this was found in France, I believe. It was the cave painting of these horses was made of charcoal. What was charcoal before it was used to draw these horses? Well, it was a tree, and the tree or some sort of plant that burned in a fire created the charcoal, and then people 30,000 years ago drew horses with charcoal. Charcoal was living, it has carbon in it. So we can take a sample, just a little tiny sample of the painting charcoals, and we can date it. We can figure out how much carbon-14 is there, how much nitrogen-14 is there. We can look at the ratio of these two things and get a very accurate age of how old these paintings, drawings are. So we've aged them to about 30,000 years. Now, carbon dating is good for things that are 50,000 years old. Once we get past 50,000, we have to use a different isotope, so we can't use carbon anymore. So we'll look at why in a second. All right, so let's say we had 50 grams of carbon-14. Pretend it's in this cup again. I have my carbon-14, it's in here, 50 grams of it. If I waited 5,730 years, I'd have 25 grams left. What happened to the other 25 grams? It's nitrogen now. It's not just gone, it doesn't just disappear, it's changed from carbon into nitrogen. So if I had 50 grams, after one half-life, I have 25 grams. After 2 half-lives, sometimes students, when they first think about this, they're like, well, 2 half-lives, it's all gone, Mr. Borden. Why are we doing this? But that's not the case. After the second half-life, you're going to lose 50% again. So half-life is the amount of time it takes for half to decay. It doesn't matter how much you start with necessarily, you're always going to lose half. So instead of half of the original 50, we're now losing half of what's left at 25. So after the second half-life, how much should we have left? What's half of 25? Help me out. We're going to go with it all the way down. $12.5. Bingo. All right, so 2 half-lives, we're down to 12.5 grams. We wait another 5,730 years. Time's ticking. What do we have left after that? What's half of 12.5? Half of 12.5, 6.25. And then another half-life passes. We wait another 5,730 years. We check out our sample again. We're down to 3.125 grams. Another half-life passes. Another 5,730 years passes. We're down to 1.625. Then we keep going, and the number is just going to get smaller and smaller and smaller. But will this ever go to 0? Will we ever have 0 left? No, it'll never disappear fully. And you can test this with your calculator. If you started with 50 and you divide it by 2. So I go 50 divided by 2, then I'm at 25. And I can just divide by 2, just keep on hitting equals, 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 and it's going to divide by 2, divide by 2. So I can go from 0.8 to 0.4, to 0.3, to 0.19, to 0.09, to 0.04, to 0.02, to 0.01, to 0.006, and it can just keep going. Now, when we're talking about samples of elements, if I had a cup with 50 grams of carbon-14 in it, there would literally be trillions and trillions and trillions of atoms in this cup. So when I'm talking about dividing the amount in half, I can just keep dividing it almost forever. But you run into a problem. So after 6 half-lives, our 50-gram sample is down to 0.8 grams left. If I do another half-life, I'm down to 0.4. If I do another half-life, I'm down to 0.2. So at a certain point, around 10-ish half-lives, the amount of sample that you have left is so small that you can't really see or can't really detect how much carbon-14 is there. Now, I use this essentially a really big number of carbon-14, 50 grams, that's a lot. If we think back to this cave painting that we could test here, this cave painting probably didn't weigh more than a gram, all that charcoal together. So we didn't scrape it all off. We just took a little tiny sample, less than a gram probably. And we can use really, really amazing mass spectrometers and things like that to figure out how much carbon-14 is in there with like very minuscule samples. So once we start getting into really old ages, the amount of carbon-14 that's left is so minuscule. We're talking like thousandths of a gram, no, less than that, like billionths of a gram. It's just minuscule amounts. All right. So here we go. When we plot this on a graph, and the graph above me here is the isotope strontium-90, all of the graphs are always going to look the same. You're going to start with 100%, and then you're going to go to 50, then 25, 12.5, 6.25, 3.125. And they're always going to follow this sort of curve, and we call it a decay curve. And they always look the same. They literally always are the same. So some decay curves will have percent, some will have mass, some will have number of half-lives on the bottom, some will have years on the bottom. But they all end up looking the same. So here's your definition of half-life. Half-life is the time required for half of the radioactive sample to decay. which is not a great definition. I don't like this definition because when we just talk about something decaying, it just kind of takes the what it's turning into right out of the equation. So like the graph, strontium 90, I have my fancy sheet here, my data book. Strontium 90, it's not even on this one. I don't know what strontium 90 turns into. Anyways, carbon 14. Let's go back to carbon. Carbon 14 changes into nitrogen 14. So as the amount of carbon decreases, let's say I start with 0 nitrogen, all carbon 14, 1 half-life, I have 50-50. After 2 half-lives, my carbon 14 is now down at 25%, but my nitrogen's up at 75%. And then I do another half-life, I have 12.5%, and then 87.5%. And you just get, as one decays, it's changing into something else. So if you start with 0, 100, 1 half-life's 50-50, then you get to the 25, 75, and you just keep on getting further and further apart. So half-life, beside me here, Costin, the time required for half of the sample to decay. So the specific example we're looking at here is strontium 90. Has a half-life of 29 years. So different elements, different isotopes have different half-lives. Carbon 14 has a half-life of 5,730 years. It's a long time. Strontium 90 has a half-life of 29 days. So every 29 days, see down at the bottom here, every 29 days we're going to have half. So after the first half-life, 29 days, we're at 50%. After our second half-life, it's at 58 days, we're down to another 50%, or 25 of our original, or 2.5 grams, because we started with 10. And this just keeps going. So essentially all these graphs are going to look identical to this. It's always this nice sloping curve that kind of never really gets down to 0. You're always going to have just a little bit there. All right, so the example we included here at the very beginning, we had 50 grams of carbon 14. After 5,730 years, 1 half-life, we end up with half of that, so 25 grams. And we can talk in terms of time, we can talk in terms of half-life. So some graphs will have time, some graphs will have half-life on the x-axis or the bottom axis. And then we can talk about grams, or we can talk about percentage. So we can talk about the actual mass that's there, or we can talk about the percent of what we have left at each one. And the good thing about the percent, it's always going to be the same. You're going to start with 100, then you're going to go to 50, then 25, then 12.5, then 6.25, then 3.125. And then mass, you can start with a different mass, just depends on the question. So this mass, we initially started at 50, then we went to 25, then we went to 12.5, then we went to 6.25, then we went to 3.125. Always dividing in half each time. Half-lives go up. You start at 0 always. After 1 half-life, you've got half left. 2 half-lives, another half. 3 half-lives, take a half. 4 half-lives, take a half. So I believe in the learning guide, it asks you to draw a table kind of like that. Somewhere, maybe not. Nope. So this type of graph is called exponential decay. It starts off, it drops really, really fast, and then it starts to slow down as you get closer to the x-axis or the bottom axis. Now, one thing we can talk about like carbon dating, but if we just want to talk about using isotopes in general to find out how old things are, we call it radioisotope dating or radioactive dating, just to generalize for all isotopes. So we don't always use carbon. If something's older than 50,000 years, Carbon's no longer good. It's almost all decayed. There's so little left that it's hard to really detect how much is there. If let's look at these graphs here first. So this first graph is mass on the side and then number of half-lives on the bottom. If we look at the next graph, it's almost the exact same, but now we're talking about percentage versus number of years. So the graph, the curve looks exactly the same. It doesn't matter what we use to plot the data. And we can use any combination of percentage and mass and time and half-lives. So this first graph has mass of sample and then half-lives on the bottom. I could continue to plot mass and then I could have time along the bottom. Or I could do like percentage and half-lives along the bottom. So we can just kind of pick and choose depending on the information we're given. So I've mentioned this already, but why is carbon-14 dated only good for 10 half-lives? So we can see that this kind of radioactive decay or this exponential decay, it drops off really fast. We go from 100 to 50 to 12 and a half, 6, then we're down to 3, then we're down to 1, we're down to 0.75, and like once we get down here, we're so small. So this is 1 half-life at this dot, this is 2 half-lives, 3 half-lives, 4, 5, 6, 7, 8, 9. So after about 9 half-lives, 10 half-lives, the amount of sample is just so small, it's really hard to measure anything at that point. We're getting better. We have really accurate dating technology now, but there's just so little left. And that is the same for all isotopes. Now, when I say all isotopes, I mean all isotopes have different half-lives, the different lengths of time. Some have half-lives that are fractions of a second, and some have half-lives that are billions of years. And we just need to pick the right element to figure out exactly how old something is. So this chart is almost the same as the chart that is in your data booklet on page 12 here. You have this common isotope pairs chart. And when we start with something, we call it the parent. And the parent is decaying into the daughter. I don't know why they chose the combination parent and daughter. It's just what they've used in science. So the parent isotope is what you start with. That's your original radioactive material. And the daughter is what it's decaying into. So if we talk about carbon-14, because that's a really important one for life on Earth, carbon-14 is decaying into nitrogen-14. It actually emits a beta particle to get from carbon-14 to nitrogen-14. So at nitrogen-14, it's stable. And that takes 5,730 years. We can do that for about 50,000 years. So if something's older than 50,000 years, then we can't use carbon anymore. Uranium-235 has a half-life of 710 million years. That's a long time. If we take 10 half-lives, we're looking at about, what's that, 7 billion years. So anything older than 10 million years, we can use the uranium-235 method. Potassium is the parent, argon's the daughter. That one takes 1.3 billion years. And then right at the bottom of the chart, you have rubidium-87 decaying into strontium-87, and that takes 47 billion years. How old is Earth and our solar system? Anybody have a date on that? Very, very old. Yeah, we're talking 4.5 to 5 billion years. So something like rubidium breaking down into strontium or decaying into strontium is 47 billion years. That's a really, really long time. So we can't, like rubidium hasn't gone through a full half-life. Some atoms will decay, but not half because it just takes so long. 47 billion years, we won't be around anymore for one half-life to occur. So some things are really, really long, some things are really, really short, and it just depends on the isotope. So carbon-14 decays into nitrogen-14 in one step. It emits one beta particle, it goes from carbon to nitrogen. Done. If you look at something like uranium-235, that takes 15 steps. So it'll change from uranium-235 into, I think, polonium, and then it goes back to uranium, and then it goes back to a different isotope of polonium, and then it goes like down, and it'll eventually end up as lead. But it takes 15 steps to get there. Thorium-235 to lead-208 in 10 steps. So you'll find that most really heavy radioactive elements find somewhere stable around lead, around 208, and lead is kind of one of the heaviest stable elements. So potassium is another good one that we use often. And potassium breaks down into argon, and we call it the potassium-argon clock because we're using these isotope decays to measure time. Has a half-life of 1.3 billion years. And this graph's really great at showing the potassium, the blue line, as it goes down, it's mirrored by this red line. So as the amount of potassium decreases, the amount of argon increases. Originally we start with 0 argon. Our sample is all potassium. And then after a little bit of time happens, we end up with argon being produced. And then at 1.3 billion years, we have 50% of our original sample is decayed, so we have a 50-50. And then I think these numbers are wrong. This should be 750 here. This is a typo in the textbook, essentially. So it should be 750, so you go from 500, 750, 875, and so on. So this is how potassium breaks down or decays. I shouldn't say breaks down, that's not the right word. This is how potassium decays into argon. And you can see that you can look at it in a chart. You can talk about it in terms of half-lives. You can talk about it in terms of time. You can talk about the sample size. You start with 1,000, then 500, half again, half again, half again. And then argon starts at 0. Then I get 500, 750, 875. And then you could look at a ratio. But this isn't quite as common, the ratio. I think this is the only time you'll see it. What's 9? It's a number, Costin. It's a number. Learning guide number 9. That's what you're at. 5, 6, 7, 8, 9. Use your data booklet to determine what parent-daughter isotope pair is represented by the graph above. Okay, we'll look at that one later. We're not quite there yet. I think there's a couple more slides. Maybe we're done. Let's see. Yeah, that's it. All right, so what I like to do at this point, and I don't know, some of you guys have Macs out there. I think Madison and Jesse both use Macs. So sometimes it doesn't work, but I've had Mac students run it. I don't know what the deal is with Macs and Java, Mac's hatred of Java. But in the course, there is find the right unit, there we go. There's the half-life section, so we've kind of just touched on a lot of the half-life stuff. And then there's a half-life assignment. And if you click on the half-life assignment and you click on the download button, there is just a Word document that'll download. And it is some questions that go along with kind of a simulated decay experiment type thing. And the first few questions are just some basic vocabulary like neutron, radioactive dating, half-life, things that we've encountered already. And then it gives you some instructions on how to use the sort of the decay tool. So in Moodle, it says click to run, and this normally appears on the actual little thumbnail here. So if you click on the thumbnail, it should launch your Java application, and you say, yeah, I want to keep it, and then you click on it, and then it launches Java. So this little activity, I'll go through here. There we go. All right, so what we can do here is we can pick different isotopes over above my head here. And the first one we'll want to look at is the carbon breaking down into nitrogen. So what I'm going to do is just click on the little bucket here, and where it says add 10 down at the bottom, and click on that a few times. Oops, I'm going to pause that. I'm going to reset it. All right, so I've added a few atoms of carbon-14. So these atoms of carbon-14 are my sample. And I'm going to watch what happens as my sample decays. So if I click play, I can go step by step. So as time goes on, you can see that right over here on the side, this carbon just decayed into nitrogen. It just changed. It emitted a beta particle. It became nitrogen. So I'll just keep going, keep plugging along. Oh, this one's decaying, and this guy over here is now decaying as time goes on. So I can just do it a step at a time. And you can see that after my half-life, 5,730 years, half of my sample, my carbon-14, has decayed into nitrogen-14. And then if I allow this to continue for another 5,730 years, so around here somewhere, I should only have about 25% left. And that's probably the second half-life there. So yeah, I've kind of run low on carbon-14. Most of it's just the stable nitrogen. So up at the top here, you get a chart. So I'm going to reset this again. And you can see that the chart shows you kind of the pie of how much carbon you have. When you get to the half-life point, technically this should be about 50-50. Now it doesn't always work exactly, just because, pause it there. So yeah, there you go, it's almost exactly 50, oh it is exactly 15-15. So what you can do is, you can do that, you can look at different isotopes, you can change to uranium-238 if you want. You can play the same little game with uranium-238 and watch it decay. The half-life of uranium is now in the billions of years, not thousands of years. Half-life uranium-238 is 4.5 billion years. And then you can make your own custom one, and you can put the half-life wherever you want. So you can make a really short half-life in seconds, or you can really long half-life in seconds. So let's make our half-life 2 seconds. So at 2 seconds, you're going to end up with about half decayed. So that's the first part. The second part is the decay rates. And you just scroll the slider across and you press play, and you can watch the red guys, the red carbon, decay into blue nitrogen. So this is another portion of it. You just use the slider here to control how much you start with. There you go. So you can see as time goes, you still have a few atoms left. These red guys, there's few and far between, and eventually the sample will just be so small you can't find them anymore. So that is the decay rates one, where you're going to be asked to draw these little graphs, these decay curves. Then you have the measurement one, where you can plant your tree, and then you're going to have to kill your tree. And once you kill your tree, you can measure the amount of carbon. So you'll notice at the graph at the top, when the tree was still alive, I had 100% carbon-14. My whole sample is there, but once my tree died, now the sample can decay because I'm no longer replenishing the carbon. And it shows you the amount. This is your little measuring device here. You see the amount that's in there. And then the last one's the radioactive dating game, where you can use the little measurement tool to look at how much carbon-14 is in each of these samples, and you can figure out the ages of things based on the half-life of it. Gives you the half-life here. You can estimate the ages of things because you know how many half-lives have elapsed. So that is the activity in a nutshell. Jesse and Madison, do you mind going and see if you guys can run that just in the next few minutes here? And I just want to make sure it works. Sometimes people with Macs have no issues with it, and sometimes people with Macs have many issues with it, and I never know what the problem is. I'm not a Mac guy, sadly, so I don't understand why these things work and don't work sometimes. All right, Costin, you had a question on number 9 out of the learning guides. We'll go back there. Number 9. Number 9. All right, Costin, so this is the graph we're looking at here. Let's see if my pen's decided to work. It's a negative on the pen. Up the difficulty level just a little bit. That's okay. We'll use the mouse. So what I want to do here, Costin, is what is the half-life of the isotope represented by the graph above? So when we talk about half-life, we're talking about the amount of time half of your sample is going to take to decay. Madison, you could just say okay to it, and I promise you it won't harm your computer, even if it warns you. Yeah, that's right, Jesse, half-life assignment. So Costin, what I'm doing here is on question number 9, I'm starting with 100%, and then I want to look at when my parent reaches 50%, and that's right here. So here's my little dot, and I'm going to go down, and I'm going to look at where I'm crossing this axis here on the bottom. So down here, this looks like this is time in billions of years. So this is 20 billion here. Right here, I'm going to guess at maybe like 16 billion or so. Looks like about 16 to me. So what is the half-life of the isotope? It looks like it's at about 16 billion years. I'm not going to write in 6 billion, but I'll write the 16 down. Is this not number 9? Oh, 8, 9. No worries. It's a kind of a two-step deal. We can't do the one without the other, Costin. So once we figure out the half-life, Madison, it's trusted source. I assure you it's not going to harm your computer. If it does, I'll buy you a new computer, promise. I haven't put a virus into the course. No go for you, Jesse? All right. I'll have to come up with another plan for you. All right, so 16 billion years. Let's get back to this. What I can do now, Costin, once I figure out the length of time the half-life takes, I can go to the common isotopes pairs chart on page 12 of your data booklet, which kind of looks like the one in the notes. So I'm going to jump to the one in the notes because I have it accessible. Wrong one. All right, so this is the common isotopes pairs chart. Looks almost the same as the one in your data booklet. So I said it was about, 16 billion years from the graph, right? That's what I found, the 50%, and I dropped it right down, and I said, okay, that looks like about 16 or so. If I look down at the very bottom here, the closest to 16 billion is the 14 billion. My cursor won't go quite as far as I need it to there, but down here at the bottom, thorium-235 changing into lead-208 is at 14 billion. So that's about as close as I'm going to get. I'm nowhere near 47 billion, 4.5 billion, no. The others are in millions and thousands, so that's just not going to work. Thanks, Madison, for having a look at that. So yeah, the closest is the thorium-235. So what I'm going to do is I'll go back to my learning guide, And I looked in my learning guide, or my data booklet, and it's thorium. Thorium. I'll give you the symbol, thorium 235. Oy. So the reason I needed to do 8 was to figure out the half-life in years, and then once I found it in years, then I could go on to 9 and figure out which one was, the closest to the one I found there. Anybody else running a Mac out there in Macland? Just Madison and Jesse and Connor. The 3 of you have Macs. Do you have access to PC at home? Or is it just Mac and only Mac? All Mac all the time. Okay, so I'll send you guys a message. I do have to, that's all good. Just Macs. Okay, so I'll get you 3 guys sorted. Apple, yeah. I'll send you guys messages. So for the rest of you, have a go at the learning guide questions. There are some, tricky ones in there for sure. And just kind of do your best. Some of them ask you to draw charts and tables and stuff. And I'll get you guys to just try your best there. We'll talk about it next day. I'd also like you to attempt the activity there. For some of you with Macs, it's going to be impossible. For the rest of you, just go through the instructions. It's generally pretty straightforward. Students don't have a difficult time with it. But if you do run into issues, we'll talk about it a little further next day. So finish up 7.2 in the learning guide. Have a go at the radioactive decay worksheet. And I'm going to leave you guys there for now. No activity on Friday tomorrow because of Pro D Day. So have a great weekend, long weekend, and I won't see you guys till Tuesday morning. So take care, and we'll see you. Is there something today? There's a museum tour at, I don't know what time it is. It's behind the scenes at the museum. I didn't think it really applied very well to us. But if you're interested, send me a message and I can find out the exact time that happens at. So I will sign off for now. Have a great afternoon. Have a great long weekend, and we'll see you bright and early on Tuesday. Thanks.